looks like that? Because it's the Catalina, it's Max operating systems are called, they're like some landmark.
I'm finding out what all my colleagues are doing.
Yeah.
You say Thompson, I just think cavity QED.
Oh, yeah. No,
Okay, how many students have I had who are working on this fraction plot?
oh, yes, yeah, I believe it. Yeah, no, I visited here to give a colloquium. Oh, yeah, okay.
I had your name written on the blackboard for about 6 months to
Ah,
look at your papers, and
nice.
I erased the blackboard.
Nice. Those are the two. That and Tazi 16 years ago. I was,
What year,
I want to say 2000. It was probably 5.
yeah, they get vague after a while.
Yes, it's been a while.
People walk up and say,
Yeah, I remember you very well. So.
of course, yeah.
So. I should start? Okay. All right. Okay, so let's get started. Sorry you have me 3 times in a row. I hope you don't hate the sound of my voice by the end of this. So remember at the end of the last lecture, we talked about how to look for ultralight dark matter coupling with certain kinds of coupling, in particular coupling direct to operators of the standard model, right? Like the electron mass or the fine structure constant, things like that, right? And this was the slide I showed the last time where you could look for new forces. For example, we also talked about using atomic clocks to look for that kind of dark matter. That's really, though, only one possible class of couplings. I would call that one possible kind of class of signatures of ultralight dark matter. So what I wanted to start with today was to try to classify for you all, or let's say most of the leading order operators for ultralight dark matter. So, sorry. So we can use the tools of effective field theory, right? If I believe the laws of quantum field theory, if I believe the symmetries of the standard model are good and apply to the dark sector as well, and I believe Lorentz invariance, things like that, then really there aren't too many possible different leading order ways the dark matter can couple. So I'll only talk about leading order, by which I mean, for example, I'll just take the dark matter field to the 1. No higher powers the dark matter field. Of course, if you forbid that linear coupling of the dark matter, then absolutely, quadratic couplings can be very relevant, and there's been a lot of interesting papers written about that. But there's only so many things I can say in 1 or 2 lectures. So then it's very nice. You might think, oh, look, I can write down any model I want, but really, any model I write down, let's say for this ultralight dark matter, if it's constrained by these laws, there aren't too many different low-energy effective field theories, low-energy effective couplings that could possibly be allowed, that could together sort of quantify all the possible UV physics that's going on. Whatever complicated stuff is going on in the UV, if I just want to detect it in my lab, I just want to know, what's the low-energy effective coupling of it to the standard model. Okay? So let me start by dividing them up. So we said yesterday it has to be a boson, so either scalar or vector. You could try to make a spin too, actually, but that theory is even harder to write down. And then as someone had sort of hypothesized yesterday, let me divide them up by their CP properties. So the scalar divides into the CP odd pseudoscalar, for which we often use the word axion, or the CP even scalar, for which I sometimes use the word axion as well. As I mentioned yesterday, really, I would expect all particles to have all couplings, since CP is actually not a good symmetry of the standard model. However, they will tend to dominantly fall in one class or the other, because CP is a pretty good symmetry of the standard model, unless I broke in the dark sector. And similarly, for vectors, they could be CP even vector or CP odd axial vector. And then I can just write down all the possible couplings to standard model fields. I'll just focus on standard model fields that I think there's a hope of detecting. Although, by all means, if you come up with other ideas, great for looking for other kinds of fields. But so, for example, the axion can couple to E and M through this operator. So I'm going to write down A for the axion field and F for the field strength of E and M. So A coupling to FF dual. We'll talk about that more in this lecture and the next lecture. It can couple to the strong force, QCD, through now here, G is the field strength of QCD, so to GG dual. And I can also couple directly to any fermion fields in the standard model, electrons, quarks, or nucleons, et cetera, through this kind of operator where psi stands for the electron or the nucleon or whatever. And this, as we'll talk about in just a second, is a direct coupling of the axion to the spin of the particle. So you'll have spin signatures, which are often very nice things to look for in high precision experiments. Or it could be a scalar. This is what I talked about the last 2 lectures. So it could couple direct to by this O. And now I'm writing phi for the scalar, I guess, just to be confusing. Sorry, I should have written A again. But so phi now stands for the dark matter here. And this OSM means any operator of the standard model, right? So long as phi is neutral, then it can couple to any operator of the standard model. For example, yesterday I wrote the electron mass, but we could write any other operator, right? It could couple to the charge, whatever. Or also it can couple, one of my personal favorites was straight to the Higgs quadratic, since this was the coupling that gives the Relaxion model that I liked, if you're familiar with that. This coupling might look a little different, but if you work through the consequences, you'll see actually all of these couplings do essentially the same thing. So for example, coupling direct to the Higgs like this, when the field oscillates, after I go to the low energy theory of the standard model, all it's really doing at low energies, the effect I can look for, is also oscillating, sort of acting a lot like this, oscillating, for example, the electron mass or things like that. Okay? So I would look for all of this class of operators with that same kind of types of experiments that I was talking about the last 2 lectures. Okay. Is this clear so far? Any questions so far? Questions on what I'm doing? Yes?
When you say phi, it's like represented by phi squared.
Could be, yes. Absolutely, that's right. I've mostly been talking about the leading order phi to the 1. Absolutely. That will tend to be the largest operator unless I forbid it with some Z2 symmetry or something. But that's right. You could couple even phi squared, direct, and things like that. Good, yes?
Is the coupling the spin coming from the d mu part or the gamma mu gamma phi part?
Is it coupling from the B mu part of the gamma mu gamma 5? Is that what you said? Or
D mu.
the D nu? Sorry,
Yeah.
the D nu.
Yeah.
Yes, if by that you mean it'll depend on a derivative of the axion field, then yeah. In fact, I'm going to show you this in just a second, which might answer the question more directly. But yeah, I mean, spin has a direction, so it has to couple to something that has a direction. It can't couple direct to the axion, because the axion of the scalar has no direction, so that doesn't work. It doesn't satisfy Lorentz symmetry. So it's got to couple to something with a direction, the derivative of the axion.
So if I looked at the operator, like for the scalar case, d mu a, psi bar, gamma psi with no gamma phi. Would that
For the scalar case,
scalar case, would that have, I guess that would have different spin properties, right?
it would be a higher dimension operator than the ones I'm talking about. That's right. It wouldn't be this direct coupling to spin like this, and it'll be higher. Sorry, I should say it belongs in this class. It'll be higher dimension than these kind of operators that I was talking about. Absolutely. So I generally haven't considered it. I'm not. Let me leave it at that. I'm not aware of it having other kinds of. I'm going to list here the sort of phenomenological consequences we can look for. I'm not aware of it producing a new class of things, but you never know. That's worth thinking about. Generally, if that's allowed, you would expect probably a more important operator to be allowed, but. I don't know. I mean, that's could be a model-dependent statement. So.
Sure. So whenever you see gamma 5, you always see weird spin things happen. So that's one reason I'm thinking about it.
That's right. The gamma 5 is what gives the spin. Absolutely. That's right. If I just write down the gamma mu, but then if I just write down the gamma mu, I need the d mu, and then that would be a higher dimension than what I'm writing here, which has no derivative. Yeah. But might do something interesting. You never know. Good. Yeah. Great questions. Yes.
Sorry. You've already said this. Is it possible to have like a sort of Chern-Simons type term? I've seen I don't know if that's a thing for like axions, but we have a coupling that looks like F wedge F and stuff like that.
That's that. Yeah. That's an FF dual. Yeah. Sorry. I just read it as FF dual. Sorry. Exactly. Absolutely. So that's a classic. Exactly. For the vector, I have it turns out, actually nearly mirror set of possibilities. That's not completely obvious, but this set of operators will do essentially the same phenomenological things as this set. So I actually mostly won't talk about the vector, because almost everything I say for the scalar can just be, any experiment we propose for a scalar can almost be ported directly to some coupling of the vector. So for example, the vector can talk directly to E and M. Here, the F prime now stands for the field strength of the dark matter, and F is the field strength of E and M. I don't know why I included indices on these. So this is direct dark matter photon mixing, and we'll have some similar effects to this one, as I'll discuss. Similarly, the axial vector can couple direct to the spin of the particle. There is one sort of new thing the vector can do, which is the fermion, the matter particles of the standard model might be just directly charged under this new vector A prime. Okay? Actually, we already mentioned one of those possibilities, this B minus L coupled vector yesterday. In fact, that's one of the only or very, very few anomaly-free possibilities, as you probably know, for the ways the standard model fields could be charged. What do these do? Well, as I said, so I can look for all of these, as I discussed the last 2 lectures, using clocks, accelerometers, gravitational wave detectors, etc. I tend to call these sort of scalar couplings. These, in red here, in particular, let's say this one, and these are direct couplings to the spin of the particle. I should have said, sorry, this is a coupling of the dark matter as a dipole moment coupling. So this is as if, let's say this is the electron field. This is as if the electron has some dipole moment under the dark gauge field. Okay, another allowed coupling. Either way, this will couple the vector, or here the scalar, to the spin of the particle. And we got spin signatures that I'm about to talk about. The fact that QCD gives you spin signatures may be not so obvious, and I'll hopefully get a chance to mention that next lecture. And then finally, I would say the sort of third class of possible phenomenological consequences we can look for, so possible types of experiments we can look for. And I'm grouping many experiments together in these classes, which maybe isn't a totally fair classification, but to try to give some intuition for them, is the direct coupling of the dark matter to E and M. And I sort of pull that one out because, of course, in the lab, we're really good at manipulating electromagnetic fields and measuring electromagnetic fields. So that gives rise to a whole big class of experiments using high-precision electromagnetic measurements to look for the dark matter. Okay, and I'll talk about those a little bit later today. Okay, so this is kind of a breakdown of all the possible ways the leading order ways our ultralight dark matter could couple, consistent with effective field theory and symmetries and so on. And then we're kind of going to go through the rest of the ones that we haven't talked about yet. So is this clear? Questions on that? All right. Sorry, if I do want to take parity or I don't? If I don't? Good. In principle, absolutely. A scalar could have all of these classes of couplings, for sure. Parity is, of course, a pretty good symmetry of the standard model. So if I try to have only one class of couplings, to go to the other type of phenomena, the other class of couplings, just at loop levels, using loops, costs me a lot. So although the operator I would expect to be there, so even the regular QCD axion, if you're familiar with it, which would be a pseudoscalar, so I'll mention a little later, would actually have scalar properties and would give forces and things like that. But those would be quite suppressed. So the fact that CP is a pretty good symmetry of the standard model makes this a fairly interesting way to divide up the operators. Did that answer the question? Or? But yeah, in principle, I could write. I personally certainly have written down theories that had all of the above. Our Axion theory, for example, was an example of that.
In this theory, you were assuming that this vector is abelian. From abelian, you have extra physics.
Yeah, that's right. So this, for example, would not work. That's right. So these are possible ones, but not always allowed. Absolutely. Yes. Good. Very good. Okay. So now we've talked about those kind of scalar couplings in purple. Now what about these spin couplings? So let's imagine, for example, that I have some dark matter. Now I'll write it as A to be confusing. Coupled to the spin of the nucleon. Okay? Now, when I say this is coupled to the spin, we just had a question, so what does that mean? An easy way to see this, and relevant for us, let me reduce to the low energy effective Hamiltonian. If you write this coupling in Lagrangian and then write the low energy non-relativistic effective Hamiltonian for this, which is what I care about for atomic physics experiments or any high precision experiment in the lab, it's not operating at relativistic energies usually, although I'll give you one exception. But usually I can just write the low energy non-relativistic Hamiltonian term for this. So you can try it. It'll be an exercise from a field theory textbook. I'll leave that as an exercise to the listener. And the answer is that it looks like this. It's got the coupling, then it's got the gradient of the Axion dark matter field dotted into the spin of the nucleon. Okay, and that just comes from these gamma matrices. As I said, this gamma 5, for example, gives you that spin coupling. Yes?
Are you interested in couplings to nucleons because those are the super high precision experiments?
Yes, definitely, although also electrons would be interesting. I sort of picked this out as one example, for sure. In general, in principle, this might couple this way to any and every matter particle of the Standard Model. But, would be hard to look for taus in a high precision experiment. Well, let me say that not as a theorem. Maybe someone will come up with a great idea to look for this coupling to the tau boson or something, the tau fermion. But anyway. But yeah, we will have excellent ways to look at nuclear spin, absolutely, as I've sort of hinted over there with my NMR.
So there's not a theoretical reason specifically to look at coupling to nucleons. The experiment.
If one was there, I would expect all the couplings to be there. I would expect it to couple to all the quarks and all the leptons. If nothing else, at roughly the same level, although you could certainly make theories that violate that sort of crude guess. Good, yeah, good question. Other questions? Okay. All right, so you have this direct coupling to the spin of the fermion, whatever fermion I'm talking about. So now I could ask you the same question we asked yesterday. What does this do? What does this look like in the lab? Okay, how could I look for this? And in particular, let me say the following. Let's say I can take some nucleon, and you'll notice. So this gives me a direction. This has still got that same gradient of the dark matter field that I talked about yesterday. So maybe right here in the room, the gradient of A is pointing that way or something. Okay? So let's say I want to compare a nucleon which is spin up along that way to spin down along that same direction. Okay? So spin up to spin down along the direction provided by this gradient of the local dark matter field. Okay? What would happen? What would happen? What would that look like? And can you think of a way to look for that? So take maybe just 1 minute and talk with your partner and see if you come up with talk with the person next to you, see if you can come up with a way, or see what do you notice about spin up versus spin down?
Well, if they're perfectly aligned with the Axion field of the line and the other is something with up and down spin. Oh, it's
And also we don't know which we have
Yeah, it's gonna go this way then.
All right. Sorry if I didn't give you enough time. Babe, let me tell you what I'm thinking for how to look for this, or what some of the ideas people have thought of over the years for how to look for this. Although maybe you'll come up with a new idea, a different idea, which would be great. So one good analogy for thinking about the physical effects of this is, look, you may recognize this from your undergraduate quantum mechanics class, right? This looks a lot like, or exactly like, the coupling of the nucleon spin to a magnetic field, right? The nucleon spin has some magnetic moment. It couples like mu naught b, right? The magnetic moment of the nucleon, which is proportional to its spin, dotted into the magnetic field. So this here looks like some effective magnetic field. Okay, so first, is that clear? Remember that? Is that clear what I'm saying? All right, but don't be fooled. This is sometimes a tricky thing. It's an effective magnetic field for nucleons' spins, not for the monopole charge of the nucleon. Yeah, it doesn't give a QV cross B force. That's very important for many of the experiments I'm going to talk about. Okay, it only acts on the nucleon spin. So don't get too confused by the words effective magnetic field. Yeah. Okay, so but what does it do? Right. Well, if I have spin up along a magnetic field versus spin down along a magnetic field, I'm going to have some energy splitting, right? And in that case, you can see, of course, I mean, that right there is the size of the energy splitting, G times del A, right? Okay, or I should say that's the rough size. Sorry. Is that clear? Questions on that? Okay. Yes.
This is constantly flipping the sign.
Absolutely, that's right. So as usual, this is an oscillating energy splitting. Absolutely. In fact, let me write that. Perfect. So this energy splitting, of course, we said it goes like G del A. And remember, we said yesterday, we figured out a formula for del A, right? It was just this. Sorry, where did my formula go? It was just this. So let's say del A is roughly root rho dark matter, right? Times the velocity of dark matter, right? Remember this gradient brought out mv, the mass of dark matter times the velocity, and then the mass of dark matter times the amplitude of the A field, that was the square root of the energy density in dark matter, right? Remember that from yesterday? All right, so I know then how big this energy splitting is that I'm looking for, right? So what can I do? Well, we just talked a lot yesterday about how to look for energy splittings between two states of an atom, right? Here, it's not maybe ground and excited electronic energy levels, but I absolutely can do similar fancy AMO tricks, okay, to split an atom into a superposition of spin up and spin down. Same sort of thing, okay? So if I do that, let's say I have my atom and they all start in state up, in spin up, then I can apply a beam splitter again, and split it into a combination up plus down. Yes?
Are you using a mass in the denominator of that rho?
This gradient brings out an MV. Sorry, so this is like, yeah, and then I use the M and the A naught to make a root rho. Good, yes. Yeah, other questions? Sorry. Yes? Yes. Thank you. Thank you. That's very important. Absolutely. That's kind of the whole point. Can't forget that. Very good. Yeah, thank you. Other questions / corrections? Good. All right, so if I take it out and I split it into up plus down, what's going to happen? Well, you know what's going to happen. We just talked about it yesterday, right? They'll pick up a phase relative to each other, right? Another in other spin language, you can say I've put it in spin X and then it precesses. Same thing, right? So after I wait some certain amount of time, I'll pick up some e to the I delta ET here, right? And then as we talked about yesterday, that's something I can measure in an atom interferometer, for example, okay? So then I would just literally, here's my delta E. If I just literally multiply that by T, maybe I'm able to run a shot for 1 second or 10 seconds. So you could just literally plug in the numbers we discussed yesterday, right, for these, multiplied by 1 second, and then you know the strength of the size of the phase shift. And then you could just compare that to root n, number of atoms you put through the experiment, and then you know whether this works or not, okay? Or really, you know the sensitivity to this coupling G, all right? Yes?
Is V still going to be the variable velocity?
Mm-hmm, V is still 10 to the minus 3, the variable velocity, exactly. Yes? Am I assuming, say it a little louder, sorry? Yes, this one has a cosine MT, yes. And sorry, am I assuming that what? Very good. Yeah, good. So that's a good point. Sorry, thank you. I should have said. So absolutely. So for example, I just gave you an example. Let's say for this delta E times T, I want to evaluate it. Maybe I put in all these numbers, GANN, V, root rho, and then I put in times 1 second. Well, exactly as he says, well, no, that's not kosher. That's not fair. If this thing is going to oscillate faster than 1 second period, right? If this oscillates at megahertz, integrating for 1 second in just this simple-minded protocol is not going to do me any good. It's going to go positive, negative, right? Phase shift will flip back and forth, and I don't add anything up at all, right? You see that? So absolutely, I have to make thank you, that's a very important point. I have to make an experiment that's right for my frequency range. Okay, so here I was imagining, without actually saying it at all, sorry, that I was working in a sort of fairly low frequency range, so that the limiting thing was going to be however long I can hold my atoms coherently in this state. But absolutely, if you try to push, let's say, past the 1 hertz frequencies to higher frequencies, at least this trivial, simple experimental protocol I just gave you would suffer. It would lose sensitivity. I could do something fancier. I could actually make like resonance sequences where I flop the atoms back and forth, for example, and add up phase longer in time, but just with this simple sequence exactly, I would lose. So that's right, absolutely. So I was assuming this was low frequency compared to whatever experimental time I was talking about. Very good, thank you. Right, yeah, exactly. This is like the spin precession rate or whatever. Yeah, exactly. Sorry, yes.
In practice, would you want to do this with ionized atoms so you wouldn't have to deal with like an Axion coupling to an electron also on top of like whatever's going on?
Good. Okay. So you could, although ionized atoms are often a lot harder to work with, or you can't work with as many of them because they do interact very strongly with each other, unlike neutral atoms. And actually, it'd be okay to have the Axion coupling to the electron as well. In fact, in some sense, that's just more. I don't care how I see it. I'm fine to see the Axion coupling electron too. But you would worry about electrons because they couple to magnetic fields, and that can be a nasty background for this kind of experiment. So that's sort of I won't do it in the lecture, but that's, if you look at the papers, that's the number one thing you first want to estimate after estimating the sort of bulk size of the signal. So to do this, you'd usually put the atom in what are called magnetically insensitive states, or work with magnetically insensitive atoms where the electron spins are all paired, for example. So you would absolutely try to get rid of that, more for the magnetic field coupling, which is very strong for electrons. Good, yes?
So even though this is just an effective magnetic field and it doesn't cause any Lorentz force, will it induce an electric field just because we have these spins flipping?
Very good. Yes, and if I have a chance, I'll probably talk about that next lecture, because that was what's the right thing to say? There are some useful signals very related to that idea that we use in experiments for sure. So let me sort of defer that, and we'll talk about something very similar in the next lecture. Yeah. Mm-hmm.
So in order to carry out this experiment, I guess you will need another atomic clock to measure the time of this experiment. But in that case, because the software can also couple to the atomic clock, so does this mean that you don't have a reliable way to measure the time?
Good. No, actually, good question. So this one's fine. Actually, in fact, what I'd really probably use, I wouldn't quite call it an atomic clock. I'd use something I'd call a comagnetometer. But I basically, like you're saying, I'd run another sequence like this, but with something that responds differently. And in fact, I said comagnetometer because here, your biggest problem is, so you'd have to go through the size of the numbers and stuff to see this, which I won't do. But your biggest problem here, as I was kind of mentioning before, would really be magnetic fields. Not so much the measurement of the time, but the measurement of the phase I didn't write, which is the actual mu B coupling with real magnetic fields. And you can work your ass off to screen them as hard as you can, blah, blah, blah. But there will always be some leaking into your experiment. And they're going to couple much more strongly than the Axion to be a terrible problem. But so what you do is, you'd run this so-called comagnetometer. So you'd run some other kind of species or some other kind of state that has a different response. All you need is that the ratio of the responses to magnetic field and Axion are not quite the same. And then I can subtract them out. So very much like the protocol you're suggesting. Yeah, exactly. Very good, yeah. All right, so sorry, let me go on for 1 second. So I was just going to put in some numbers. So if you put in numbers here, this would go like, where's my phase shift? 3 times 10 to the 8 minus 8 radians for coupling, which is 1 over 10 to the 9 GeV, and that's basically at low masses the experimental limit of this nucleon coupling. Oh, and sorry, I should have said before, maybe you've heard this term before, but we often call this the Axion wind coupling. You can sort of see why. It's coupling the spatial gradient to the axion field. Yeah, that's the momentum of the axion, like we said yesterday, right? So it's the momentum direction of the axion as it flows through the lab here. That you might call it the wind of the axion flying through, right? It's that direction which couples to the proton spin. So we call this the axion wind operator. So that's the experimental limit for this coupling at low mass. That's not a terrible fit. It's small, but it's maybe not inconceivable to look for that. Yes? On the bottom here? Yeah, let me write it bigger. One over 10 to the 9 GeV, and I write it in that way in case some of you are familiar with the famous axion bounds and all the other axion couplings as well, which are also around an F of 10 to the 9 GeV or so. Yes, sorry.
Is there no, like, does the coupling to magnetic fields mean there's no chance that we could ever hope to measure delta E equals 0 and then for the axion coupling and then a delta is non-zero? Because of the oscillation trend.
Sorry, I think I'm missing the question. So delta E 0, what do you mean?
Delta E goes like cosine mt, right?
Oh, when it passes through 0 or something?
Yeah, so I mean, we're trying to measure for a fixed phase anyway, so would that be impossible?
Yeah, well, we wouldn't be looking, that's right, we couldn't see any static offset, we'd be looking for the oscillation. So we'd be looking in our data to see, this. We'd Fourier transform our data and look for the oscillation, exactly. So we wouldn't be looking for any particular value, we'd be looking for it to oscillate in time, that's right. There's many other ways to look for this kind of coupling too. So for example, you sort of see it directly. This is in a different basis. This just looks like precession of the spin, like we said, right? So in other words, if I have, this is my axion wind, my axion momentum flowing this way, and then if I have my spin here, and the spin is pointing this way, right? Well, then it's like some effective magnetic field. This spin will precess around that magnetic field, right? Go around like this. In other words, this axion, it won't make it all the way around. This is a tiny signal, so it's a very small precession rate. But in other words, this axion will start torquing on all spins, right? And remember, I was just telling you yesterday, we can make, for example, spin polarized torsion balances to look for this torque, right? They're very good, very sensitive measures of a small torque. You polarize a whole lot of atoms together, and so you add up, you get to multiply this torque by n, your Avogadro number of atoms in your torsion balance or whatever, okay? Or for example, as a way I will hopefully get to a chance to tell you about later, you can use all the fancy, many high precision techniques of NMR, of nuclear magnetic resonance, which I will hopefully tell you about later, so don't worry if you don't remember how that works. But that is a very well developed technology over many, many years, of course, because that is what's behind MRI machines and things like that, which we pay a lot of money for. So people have spent a lot of time really refining that technology. So NMR is a great way to read out what's happening to nuclear spins, basically, in some macroscopic sample. So there's lots of experiments like that that can look for this kind of axion wind coupling. Okay? Yes?
So this is your basically QCD axion dark matter, right?
This could absolutely be the QCD axion. It wouldn't have to be. It could be any other kind of axion. So I've been so far purposefully not mentioning that word too much.
No, because it's a coupling to nuclear spin, right? So if it is not QCD axion, like I can always write it in terms of QCD, and it can give me some theta angle, right?
Ah, very good. No, very good. Yeah, this one does not by itself give the GG dual. Although the GG dual will give an effective coupling to spin. I'll talk about that probably next lecture. So you're absolutely right that the GG dual coupling will have effects that look a heck of a lot like this, though. But this one by itself could just be any pseudoscalar Goldstone boson. For example, the fact that I wrote a nucleon here was solely because the NMR technology is very good, somewhat better than the ESR, the electron spin resonance technology. But I could have written an electron here, too.
Yeah, so okay, so if you write your electron, then I agree with these parameters because you are considering mass to be less than 10 per minus 2 kV and just like this one now. So yeah, it's not
Yeah, this could be anything. Of course, I could try to get this all the way down to the QCD axion line. And in fact, if I have time next lecture, I'll show you our NMR experiments where we hope to try to push this somewhere near the QCD axion line. But that's right. In principle, I could look anywhere in parameter space with this. Absolutely, absolutely. Good. Yes. Yeah. Good questions. Yes.
So there's an implicit assumption here of like full nuclear polarization.
Good. Are
there plans in progress on like achieving this kind of polarized state?
Yeah, absolutely. So you certainly can achieve full nuclear polarization. People have done it many times. It's not at all trivial, but the people who develop NMR have had lots of money, for medical application. However, so that's true as a general statement that humanity has created samples with fully polarized nuclear spin. However, doing it in situ in a dark matter experiment that I actually want to build, is, as you know, noticeably harder. Absolutely. So, for example, as I'll mention, our Casper collaboration and many others too are very much working on getting the polarization fraction as high as possible. In fact, if I get a chance to go through the sensitivity of the Casper experiment, exactly as you say, there will be a little factor in there, which is the polarization fraction. But it is so it depends a heck of a lot on the material I'm talking about. But for example, for xenon, it is, for example, relatively, I hate to use the word easy, but has been demonstrated many times, let's say, rather than easy, has been demonstrated many times to get essentially order 1 polarization fractions. But definitely not trivial, for sure. By the way, as an aside, if instead of using a macroscopic number, I was just talking about atom interferometry, which also might have interesting sensitivity, there I'm talking about a much smaller number of atoms, and I control their states perfectly. So there it's trivial, or sorry, it's never trivial. But there, the techniques that we already have that people have developed over the years absolutely let us get full polarization. But in a macroscopic sample, definitely much harder. Yes?
So I would presume that we don't know the direction that the axion
Right.
is going in.
Absolutely.
And the spin procession makes sense to me. But up there's a good chance that we might mitigate the coupling even further, right? Just by not aligning well. So do we just keep pointing this in different directions?
Good. You could if your experimental, which depends on your experimental setup. Actually, it's usually easiest though to suffer the cosine factor, to just pay the cosine and keep your spins oriented along whatever your experimental axis is, because it's challenging to rotate your whole big magnets that you're using to polarize and things like that. And so you just pay the cosine factor. Absolutely. But absolutely, that's right. That's definitely in there, and I did not write that for sure. When you do a real estimate, it should include it.
So in that sense, you're not actually measuring this directly, right?
You're measuring this times the cosine, right? Because so whatever, if the axion wind is pointed off of my direction, and I make this a superposition of spin this way and spin this way, then this energy splitting between two is this, but just times cosine or whatever.
That could make this even more diminutive.
Absolutely, although it would be really unlucky for it to point perpendicular. and in any experiment, I never set an absolute limit. I only set a confidence level limit, 90%, 95%, 99%, right? So at the 95% level, I can say, well, it's not going to be 5% tuned to live within 0.05 radians or whatever of perpendicular.
If we were to read one of those plots, how is that information?
We marginalize over the unknown direction.
Okay.
Yeah. Which is important. And by the way, I'm glossing over it and acting like it's trivial because that's how we theorists, when we talk to the experimentalists, we're like, oh, okay, just go add the factor in. Although then we had long email arguments about how to do things like this with certain other colleagues of ours. And so it isn't totally trivial. I can tell you more. I can tell you a few subtleties about that afterwards if you want. But roughly, it's just a cosine factor. Up to you have to do the marginalization correctly, which there was some disagreement about, as always, with statistics can sometimes be confusing. Excellent. Yes? Good. Not that I know of. No, I don't know of any. Well, sorry. Well, okay. No, except for one caveat that I'm about to say, which is effectively also coming from the time derivative. But otherwise, no. And in particular, actually, that's a great question because it leads me to the next thing I wanted to say, which is, well, as she says, this comes from the gradient. And I particularly don't like using the gradient because you pay a factor of 1,000. And that sucks. That's always a painful thing to do, right? These signals are low enough. So can I get rid of that factor of 1,000? And we thought for many years, so that's along the lines of, can I get anything from just the time derivative, which wouldn't have that factor of 1,000? And we thought for many years and said, well, that seems really hard, right? So there aren't physical effects directly in the low energy non-relativistic Lagrangian of the time derivative. So it just sucks that everything's non-relativistic. But boy, wouldn't it be nice if I could just take my whole lab and boost it to relativistic speeds? That would be great. But of course, you can't do that with an NMR setup or an atomic clock or something. So for a while we gave up. But then many years later, after we had started thinking about this, we realized that there was a precision experiment you could do that people already proposed, which is a beautiful experiment. There's this so-called proton storage ring EDM experiment. I don't know if you know about this. I really won't have time to tell you much about it, but if you don't know about it, it's a great idea, a beautiful way to look for the proton EDM. Very, very cute, very clever trick. For us, though, the basic idea is the following, that I can get rid of that V. I don't have to boost my whole lab to relativistic speeds. Instead, I can just boost the particle, the nucleon, to relativistic speeds. I won't go through this whole thing in detail. We could give a whole talk on this, but let me just tell you the sort of very basic heart of the idea, which is if I take my proton here, spin this way, and I boost it, it's in some storage ring, I boost it to relativistic speeds, well then, it doesn't even matter that the dark matter had a gradient at all. In fact, let me just theoretically set the gradient to 0. Just say there's a dead homogeneous axion field here on Earth, oscillating in time. That's it, so only an A dot in our frame. But the proton is moving boosted with respect to us, yeah, relativistically. So it absolutely has to see a gradient. I mean, just do a Lorentz transform on the vector, d mu a, yeah? D mu a in our frame has only a 0 component. When you boost, of course, it must pick up a spatial component. So then there's going to be a whopping big, if I jump to the proton's frame, I can still use this. There's going to be there's a whopping big effective magnetic field, okay? Only one problem, though. So that's great. That works for a tiny split fraction of a second. But there's only I only have so much real estate on Earth to go in a straight line. If I want to keep these things going for a long time, to integrate up over time, integrate this phase shift up over time, like we were saying over there, right? I got to keep the proton going around in a circle. And then, of course, this gradient of A, notice, is not set by any external thing now in this experiment. It's set by what direction I boosted the proton in. So if I make the proton go in a circle, the gradient of A goes in a circle. And that would, in general, completely average out my effect on very fast timescales. Okay? Do you see that basic idea? Is that clear? Yes?
Doesn't the proton frame also rotate at the same time? So the axion gradient is switching sides between the lab frame.
Okay, very good. I think what you're saying is the following, which is one way to say it is in the lab frame, you would see the proton spin would do some precession, which I think is what you're saying. The proton's frame rotates, right? Absolutely, exactly. And that's the trick we're going to use. Now let me back up. If somehow you were able to only apply a monopole force to the proton and just move it in a circle like this, then the spin would not precess. The monopole force by itself doesn't couple to the spin, and so the proton would go like this. Its spin like this, its velocity like this, and the velocity would keep turning as you go in a circle, but the spin would just go like this. Sort of like the Earth going around the sun, the Earth's spin doesn't change as it goes around the sun, right? That's just gravity, is just the monopole force. Well, the gravitomagnetic thing is very small. However, that's not how we move protons in a circle. We don't move them with gravity or our hand or something. We apply electromagnetic fields. So exactly as he says, actually the proton spin will precess. And this is the beautiful idea of the proton EDM experiment that was proposed many years ago by other people. If you do it just right, you have to pick just the right combination of fields, okay? It has to be very finely tuned, perfectly experimentally chosen, to be what's called the frozen spin method. So you apply just the right set of electromagnetic fields that make it go in a circle and also make the spin precess at exactly the same rate that the particle moves in a circle. But then, exactly, you get the spin precessing right along with the velocity. The two remain always in a fixed relation, and then the signal adds up beautifully. So we realized the experiment they had already worked on creating for the proton EDM, I can tell you about that later if you want, why it works as a great EDM experiment, works great for this Axion wind signal, and in particular avoids this velocity suppression. So I get to improve the whole thing by 10 to the 3. And the sort of amazing thing is, usually we think of colliders as not being extremely high precision machines. They're not like atomic clocks or something. But you can put a lot of protons in the ring, and then they feed them out and can read them with some sort of squid magnetometer, for example, some high precision way to read out how much they processed. This can actually make a very high precision experiment and avoids this 10 to the 3. So it can be a very nice way to look. By the way, as an aside, you can convince yourself that you don't get any boost by gamma, though, over this. The time dilation in the proton's frame removes that. The gamma would be in the grad A, right? But it gets removed because the proton spends less time in its own rest frame. Question, sorry, yes?
So this ring has a certain period, right? This
Mm-hmm.
Is there any clever choice or any choice I must make relating to the cosine?
Great question, great question. That brings me to my next plot, okay? Which is, here's another one of these plots of the strength of this GANN coupling versus the mass or frequency of the dark matter. Here's stellar limits. This sets these 1 over 10 to the 9 GeV limits. I won't talk about stellar limits at all, but I believe that Ben Safdie will be talking about them in his lectures. And here's this fuzzy dark matter edge. This solid blue line would be the sensitivity we get from the experiment I just told you, but as he suggests, I can do a little better. I can actually resonate. So I can use this spin precession period to my advantage and not make it necessarily perfectly locked with the precession around, but actually, when you get to too high frequencies, right, I'm integrating up over too much time, so the dark matter flops in that time. But I can use this effect that at low frequencies was a pain for me. I can make the spin precess in time with the dark matter. Now, it's a resonant experiment, so to do this whole thing, I have to pick a particular frequency, sit there for a small amount of time, and then scan, switch frequencies. But absolutely, that kind of thing does help me you can see sort of parametrically better sensitivity at high frequency, for sure. Sorry if that was too fast. I mean, this is, usually I give a whole talk on this, so probably confusing, but yes.
So if you are trying to boost the photon, show that this is being a circle. In this case, the space limit is no longer decreasing because the transverse direction is not too pi r. That is the perimeter is not too pi r because you're boosting the E square. While the radius is still in the same.
Yeah.
This means it's not increasing. You should do this structure like very
Good question. So there are some geometric phase effects, although I don't think that's exactly what you're talking about. But you do have to think about those carefully when you think about the whole thing. What's the right thing to say? I think that way of phrasing it can sometimes be a little confusing because I would say the maybe better way to talk about it would be each different step along the ring is actually really a different frame. So I can't just it's not all one frame in which you're measuring this circumference and the radius. But if you like, maybe we can, that's a sort of subtle point. Maybe we can chat. And it's also it's usually just one of these confusions with language. So maybe that's the sort of thing we can talk about after the lecture, yeah. Yes?
Maybe related, but a little bit simpler question. So I'm guessing there would be some optimal radius for the protons moving around. How did you pick that, though, not knowing the values of the parameters in your Axion field?
Good. Well, so what it really is you want to do this frozen spin method. So you want to pick the parameters of the ring, which are the radius and the strength of the applied E and B fields, and the boost of the proton, to exactly make this frozen spin method work. And that's I haven't written the formula down for. I can show you afterwards if you want. But exactly, there's one exact relation between those parameters that would make this work. Well, let me not say more. It's a neat physics. You can check. It's cool physics, but let me not go into it now. But yeah, you want a particular set of parameters for the ring. But just so long as the frozen spin works, then the Axion signal will work.
Okay, so the signal would be the protons not being frozen in their spin.
Good. So I totally glossed over all the details. So as I said, normally I spend this is a whole talk. The way to do this experiment is to align the proton spin as I've shown here in the plane of the ring, whereas the way to do the EDM experiment is to align the proton spin like this. That's totally not obvious, okay? That's just to tell you there's some extra details here that I have not told you. The signal, so the frozen spin rotates the spin of the proton in this plane, like this. So this is the velocity and this is the spin, and they rotate like this. Our signal is this rotation. So we look for that one as opposed to this one. Exactly, and that's key. So that exactly what you're asking was one of the first things we had to check. Hey, is our signal really not just degenerate with or destroyed by your frozen spin method? Because of course you sort of feed back to make sure it's still frozen and things like that. Good. Okay. Sorry, that's a big long discussion that I really didn't. I'm trying to do all these experiments very quick to give you a decent number of examples here. Okay. So that was all I wanted to say about this spin coupling. Now I wanted to move on to our last two couplings and spend sort of the rest of the time we've got on them, because they're sort of big, important examples there are a lot of experiments on. And in particular, let me start with the electromagnetic coupling. So electromagnetic detection of axions. Let me go back to the slide. Oh, not there. So just to remind you, I'm talking about those operators in green there. Now this is a huge subject. This is probably where there are the most new kinds of axion ultralight dark matter experiments. So I won't even attempt to tell you about anywhere near all of the experiments. Instead, I just want to give you really a kind of brief introduction to the field, okay? And then you'll be able to go off and think about any particular experiment you want, hopefully after that. So we're talking about these operators here. So for example, the coupling of the axion to E and M. And in particular, for the experiments I'll be talking about, it's usually easier to rewrite FF dual, the field strength of E and M, as E dot B, the electric dot magnetic field. Okay? And of course, in Feynman diagrams, this is the axion coupling to two photons. All right? Or as you can see, there's this so-called dark photon, or the new vector coupling, which would be coupling between the field strengths. And if I write this out in the more useful field notation, this would be a coupling between the standard model electric field times the new electric field, for example, and similarly B times B prime. Okay? And in a Feynman diagram, this is just this hidden photon or dark photon. Oh, let me write it as A prime. Kinetically mixing, so mixed kinetic term, directly becoming an A as it propagates along, becoming a photon, quote unquote, as it propagates along. Okay, so I have this mixing between E and M and the dark matter field, whether it's a scalar or a vector. And so one classic way to look for it, for example, is by using a resonant microwave cavity, like, for example, the ADMX experiment. So let me draw my cavity as just a cylinder. So this is some resonant cylinder. And then, axion field comes in, and I make sure to apply some background B field, so some VEV of B here. And you can see what that does. If I have my background axion field, if I have some B, then it's going to be a source term for E. It's going to generate some new electric field, right? Or if you like, some new photon, or really, actually, it's not, of course, an on-shell photon. It's just some cavity excitation. It's going to drive the cavity. It's going to dump energy into the cavity. And to get as much sensitivity as possible, we make these, or they make these a resonant cavity. And then you slowly sweep the resonant frequency of the cavity. You move like a rod in the cavity or something, change the shape of the cavity. And you wait until you happen to land on whatever the dark matter mass is. I don't know what it is, right? So I have to scan as much frequency range as possible. But when you happen to land on it, then it's resonant. Then you all of a sudden get a big boost in this conversion rate. Okay? So that's sort of a basic cartoon you should keep in mind for how we might do electromagnetic detection of dark matter axions. Yes?
So for low masses, this frequency is decreasing. So would you need to sit at that frequency for a longer time for like a p-value?
Ah, very good. Yes, I'm going to talk about that a little bit. Absolutely, absolutely. Very good.
Is there a point where you have to wait just way too long at like the low mass?
When you get to too low a mass, a resonator is no longer the right way to go, in my opinion. Yes, although that even has been a statement of some disagreement in the literature. But yes, I would say for the very low frequencies, you don't build a resonant structure. That's right. It's even becomes very difficult to even build a resonant structure. Sort of part and parcel, same thing. Exactly. Very good. OK, so how do I calculate the signals in these kind of experiments? So in reality, what I have to do is take that term, throw it in Lagrangian, and ask for what are my equations of motion. I really only need the equations of motion of the E and B fields. As we said, we're not going to back react on the axion here. It's that we would be so lucky to have such a strong coupling to back react on the axion. So I don't need the axion equation of motion. I just need the E and B equations of motion, which are, of course, basically just the modified Maxwell's equations. So I just need to write down the equations of axion electrodynamics. These were, by the way, sort of famously first written down by Frank Wilczek. And they go as follows. Sorry, let me just write them down and then I'll talk about them. Del dot B still equals 0. Still no magnetic monopoles. OK, there they are. So first thing you should notice about this is basically just written down Maxwell's equations and added these three terms for the axion source. OK? And again, I'm not writing down the axion field equation, so you should think of the axion as just some background field, this A naught cosine MT that I plug in here, OK, for dark matter detection. All right, so these are the full equations, and in principle, I should really just solve these for whatever my geometry of my resonant cavity is, for example, or my, we also use LC circuits like the Abracadabra or DM radio experiment, or whatever electromagnetic structure I built. I can just solve these equations. It's some ugly Jackson problem, but you can in principle do it, right? So that's the right way, or that's sort of the real way. But it's useful to have in mind some simpler approximations. So let me tell you those, because who wants to solve these equations on the board, right? First, very often I can drop these gradient terms, yeah? Because that gradient is suppressed by V, the velocity of the dark matter. Now, not always. You should have a big, warning label. There's plenty of times I cannot drop those. Certainly any time if I boost relativistically, like we were sort of just talking about with the storage ring, for example, if I'm doing an axion production experiment, like a light through walls type of experiment, which I'll talk about a little later, where I'm radiating axions, or any sort of axion photon conversion where I'm producing relativistic axions. Of course, when things are relativistic, I can't just drop the spatial derivative and keep the time derivative. That would ruin my Lorentz invariance, right? But, so with all those caveats, hopefully you'll permit me for this lecture, however, to just ignore the gradients, all right? Then you can see these equations become much simpler. There's just one new term, OK? And the analogy that most people find very useful is, look, this term is right here next to this term. Let me just call it a new current, a new effective current, right? So all of these terms proportional to the axion, including the gradients, were new source terms. That's why I put them on the right side of Maxwell's equations, right? They were new things that drove that sourced, effectively, sort of like new currents that sourced the electromagnetic fields. And here you can see it very explicitly, right? This I'll just call some effective new current density, GA gamma gamma A dot times B, okay? And you know A dot. You know how to calculate that. So I should say, is that clear? That's sort of one of the most important points to take away from this. You see that? OK. Yes?
The fact that there's a B field in the current, is that somehow problematic? Because I would assume that there's some back reaction thing
Very good. Excellent. Exactly. That was one of the next things I wanted to say. Very good. That's right. So, of course, I've cheated a little bit. I mean, I've called this the variable over here. I've just said this is some current, but they both have B's in them. So what gives? So let me write that down. Very excellent. Good. Oh, sorry. So the question was, that effective current actually also has a B field in it. So if I was solving this as a differential equation, yeah, I mean, B is the variable I'd be solving for. so where do I get off just calling this some current that's going to source a B over here? So that was the question. Is that question clear? It's a good question. That's what I want to talk about now. Question, yes? Yeah, sorry, you saying for why I call that a current, or?
No.
Oh, sorry.
So this is just curl E, the problem with the curl E depends on the strength.
Right, exactly, yep. If you let me treat it as a current for just a second, though, let me say the following. I said, for example, in a microwave cavity experiment, I have to apply this background B, right? It's usually applied with some solenoid magnet. So there's just some vertical, for example, magnetic field running through this experiment. And so if there's just this vertical background magnetic field, then I'd say, okay, what am I claiming? I'm saying we just have some effective current running through everywhere in space, everywhere there's this magnetic field. So there's just some J effective passing through the cavity. Now, just to be clear, because sometimes this wording confuses, this is not a real current in the sense of a real standard model current. There's no electrons running, right? There's no actual charges running. It just has the same form as the current, right? But you can solve the equations in very much the same way. So you can just imagine there was some sort of magical volume current that didn't hit the walls or anything, of course, since it's not real particles, real fermions. But piercing the whole thing, and then that's a differential equation you can solve. In fact, it's already a differential equation that's in the electrodynamics textbooks, like, I don't know if it's in Jackson, but it's in many cavity textbooks, for example. But first, we should answer this question. So I'm claiming I can just write down this equation, del cross B is basically just this effective current, GA gamma gamma, times A dot times B, and I can just take this as some fixed background current and solve for my signal B. So that was his question. Why does that work? Well, look, just think perturbation theory, right? What is B? The real magnetic field is both the multi-Tesla thing that ADMX applies with a gigantic solenoid, right? And then some absurdly tiny little Axion-induced oscillating signal. The multi-Tesla thing is constant, is fixed in time. There's some absurdly tiny little oscillating Axion signal that they're going to try to pick up with their squids or their high-precision magnetometers. Okay? So B is a sum of two terms. One really big, one really small. So you know what to do. We're physicists. Immediately, perturbation theory, yeah? This term, this is already small. This has got the small number. This has got the epsilon already multiplying it, yeah? So what should I keep from here? Just the big part, right? Just the multi-Tesla constant field. There's also a little signal piece. The signal piece, of course, is exactly going to be proportional to GA gamma gamma, right? So I shouldn't keep G squared terms here. Those are going to be really small. So here I just plug in this background B naught, right? But here I want to solve for the size of the signal. And I won't actually care about the spatially uniform and temporally constant B. That's not relevant. That's not going to be sourced by this time-varying cosine in here. So here, I'm just looking for the signal field, okay? So this is the right order in perturbation theory. This is first order in perturbation. This is first order in the perturbation. This is zeroth. So did that answer the question? Is that clear? So that's really why you can think of this as some background effective current, okay? Yes?
That will break down if you run it for long enough, right? Is there any worry about, is that time scale too long, short enough that it matters, or is it long enough?
Yeah, no, exactly, that's right. This is essentially, I would say, if only it could matter, because that would mean my small perturbation has become quite, has grown larger, and that would be great. Then we would definitely have, then they would definitely have gotten their Nobel Prize for detecting the axion. But no, long before that happens, let's say their absurdly sensitive magnetometers will pick up this little field, and we'll all celebrate the detection of dark matter. So yeah, exactly. No, the signal is just absurdly tiny. Yeah. Good question. Yes?
What, I guess what mass is this for?
Good, I'm coming there. Definitely coming there. Yeah, that's an important question. Now, if I said in reality you should just calculate, okay, and I'll even, if I have time later, I'll just give you the real formula for this effective current sourcing modes in the cavity or whatever. But there is at least a nice, it's basically just dimensionful analysis, but it's a useful set of formulas to keep in mind. A nice sort of approximation here, which is, let's say I'm talking about this microwave cavity. I'll pretend ADMX or haystack or whatever it is just some cylinder. Well, where's my, then I said I want to resonantly match, right? I want to set the fundamental frequency of the cavity to the frequency of the axion, right? Well, the fundamental frequency of the cavity is some mode that looks like that. It's supposed to go to 0 on the walls, right? Some mode that looks like that, right? It is, of course, set, basically, up to order 1 factors, by roughly the size, the length scale of the cavity, right? So what that means is my resonant condition, if this is going to work at all, is that roughly L is 1 over M, right? Or if you like, 1 over L sets the frequency of the cavity mode, and so that should be matched to M, the frequency of the axion. Okay? Is that clear? So in this problem, there's really only just one length scale. I'm going to use that to cheat and just get the answer very quickly. There's just this length scale. That's it. Okay? Yes?
This is probably obvious, but that's the mass of your dark matter?
Sorry, yeah, mass of the axion or whatever. Mass of the dark matter. Yes.
And
yes.
why does it go like 1 over L?
Or let me write it like this. Maybe this is better. 1 over L, which is the resonant frequency of the cavity, right? That sets, the size of the cavity sets its resonant frequency, right? Light travel time across the cavity sets the resonant frequency. That's 1 over L. I want that to be matched to M, or I'm not going to get a big resonant boost in my signal. So in other words, the M's I'm looking for are the ones which are 1 over L. Those will be the frequencies for which I have sensitivity. So that already, if you can convert in your head, well, you can. The cavity's about this big. Light travels about 1 foot per nanosecond. So it's about a nanosecond period, so it's a gigahertz frequency. So that's the frequencies I'm looking for. Okay? Good. So there's really only one length scale in the problem. I mean, this is my variable that I want to know sensitivity in, so this is just some number. You already know how to compute A dot. B naught is however many Tesla you can throw through your experiment, and I told you yesterday how to convert Teslas to EV. So you could all just calculate this, yeah? So all you really need to know is what I should put in for this del cross. It's a derivative. It's a spatial derivative. I should put 1 over a length scale. And there's only one length scale, so that's what I'm going to put. All right? In reality, you should solve the equations, but let me not try to solve them on the board. So you can see then that this B field signal size, if I just divide by the del cross, okay, quote unquote, is roughly GA gamma gamma A dot, the applied multi-Tesla field, over M, okay? Because this del was a 1 over L, okay? Is that clear? All right. So that's roughly the right signal size, and so then let me just say, of course, I can plug in for this A dot and find the effective signal magnetic field that I'm looking for in one of these experiments go like this, right? I just plugged in for A dot, root rho, okay, and cosine MT. So that's this very tiny oscillating signal magnetic field that you're looking to resonate with, then build up. So as a rough order of magnitude, you should multiply this by Q, the quality factor of ADMX's resonator or whatever electromagnetic resonator you built. So just multiply that by Q, and then that'll tell you the size of the signal that you're piping into your squid, and then you hope your squid is sensitive enough, or whatever your magnetometer is. Okay? So that would be roughly how you estimate it. Yes?
So I guess what I'm seeing here, so when I'm off resonance, the only B field I measure is my B0. And then I scan through, find the resonance, and when I'm on it, then I see this, I guess, oscillatory behavior in my B field. That's what I'm actually seeing.
Good. In reality, you would get a small signal off resonance, but a much larger by factor of Q signal on resonance. And Q for ADMX is between, I think it's like 10 to the 5 to 10 to the 6, or most of these electromagnetic resonators are around there. So it's like, a million times larger on resonance or whatever. So it's there everywhere, but exactly, on resonance is where mostly we're interested. Actually, there's a caveat to that statement, but that's technical. Let me get into it later. Sometimes we do look off resonance, but a little bit off resonance. Good, yes. Oh, and note, someone had asked about, it does take time, so I don't actually just multiply by Q. It takes about Q periods to build up the signal Q. That's how a resonantly driven oscillator works, right? It builds up linearly in time. Yes?
So with scanning over your desired frequency range, I know that this is not done by like changing the cavity size usually, but like with some rod. How does that work?
Yeah, so absolutely. So whatever, this is it's not quite as simple as just a cylindrical cavity. Whatever shape you have, though, right, you actually solve the full cavity equations in here, and that determines your resonant frequency. And you can make some sort of smallish order 1 adjustments by just changing the geometry, by moving a rod, or however different groups have different ways of scanning the resonant frequency. If you wanted to make too big a change, of course, you have to make a different size cavity. And in fact, that kind of brings me to my next point, which is, look, we've talked about this before. This has a 1 over m in it. So boy, is that actually going to be really good at low mass? And sort of the answer famously is no. And that's kind of what I want to tell you now for the last point of the lecture. But you can already see one issue with that, right? Which is sort of exactly what she just raised, which is if I get a little bit of play, a little bit of throw in the frequency range by moving a rod, but if I really want to go to low frequencies, I just need to make a bigger cavity, yeah? I mean, you can't violate this approximate relation too much. So for example, as I was just saying, this is great at gigahertz, these microwave cavities, but let's say I want to look at megahertz. That's another perfectly good frequency for the QCD axion. Well, instead of the cavity being this big, if I go from gigahertz to megahertz, it scales linearly, right? Now, instead of a 30 centimeter cavity or something, it needs to be a 300 meter cavity. So 300 meters by 300 meters by, that's too big. I can't do that, right? So if I can't keep scaling the size of my cavity as I drop m, then this formula can't continue to hold. Okay? Is that clear? Instead, there's going to be a further suppression. All right? So let me tell you how that works. Yes?
So when you make a signal like this, you measure both the amplitude and the frequency?
In principle, yes, absolutely.
Both the and can be extracted.
The amplitude, very good. The frequency and the amplitude could be extracted, but that doesn't quite extract G unless I assume that it is all of the dark matter. But of course, the minute we have a measurement like this, that's one of the first questions we're going to ask. Is it all the dark matter? And do I know the Axion coupling? So have I learned something about the high energy physics from which the axion arises? Or not? I don't know. Many people will probably at first begin by assuming that it's all the dark matter if we ever make such a discovery. But I don't know. It's totally degenerate, yeah? And it's going to be hard to break that degeneracy. It's a good question. All right, let me very briefly tell you, if I wanted to go to lower frequencies, I can't build a 300 meter cavity. What do? I need to make some electromagnetic structure that resonates at frequencies way below the light crossing time. So that's like what you learned in your freshman E&M classes, some magnetostatic limit. So I just need some LC circuit, okay? So this is how the abracadabra or DM radio experiments work. Whoops. LC circuit by itself is no good since it would pick up all the crap that's in the environment, so I really want an LC circuit in some shield. Okay, that's the experiment in very brief. And then, of course, I'd apply some background magnetic field here, and I would get this effective current, and it would drive some oscillating signal in this. The LC circuit the electromagnetic resonator would ring it up, and I'd read it out again with some high precision magnetometer. Okay? But what signal size do I get? Well, so it turns out if you calculate with those equations, or even you can get some intuition for looking at the size of the cavity of the shield you're in and the screening currents on the walls. Let me not go through that. It's a little more complicated, but if you want, I can tell you about it later. It's roughly the same size signal. But then it has a suppression factor. It has a suppression by the size of the cavity. MA times L, that's a dimensionless number, MA times L, okay? So in particular, I can cancel the MAs and just see, okay. So it's actually, the behavior is much worse as I go to low mass. Now, like I said, you can get some intuition for this by staring at the differential equations for long enough, or you can just solve the differential equations and see that. But we actually also already knew there had to be something like that. So let me tell you why that is. We expected that. Why is that? Well, that's because this is fundamentally coming through this operator A coupled to FF dual, right? But if I look at the operator, for example, just theta FF dual, just what's so-called theta term, where this is just some constant dimensionless number, you may know this operator is famously a total derivative. It looks very roughly something like theta d of ADA, okay? Where this is the field strength of A. So it's a total derivative. So this cannot have any physical effects. This cannot possibly be observable. Small asterisk unless there were some funny boundary conditions as induced by, for example, magnetic monopoles. Let's ignore that since we don't have any of those in our lab. So basically, this doesn't have any physical effects, okay? Well, you say, but that's not my operator. My operator is A, GA. FF dual A's got dynamics, so of course this could have some physical effects. I've just been telling you about physical effects of this, yeah? But, right, in the limit, so this is, when you see A here, just think A naught cosine MT. But in the limit that frequency M goes to 0, this just goes to a constant. So in that limit, it cannot have any physical effects. All the physics must decouple. Anything observable must decouple in the M goes to 0 limit. Any effect of this operator. Do you see that? Is that clear? And that's what this extra factor is doing. That doesn't, by the way, tell me that it was this factor to the 1. It just tells me there was some powers of this factor. But it is, in fact, this factor to the 1. Okay? Is that clear? Now, one last thing you might object, because actually these masses cancel. You might say, wait, I just told you that this is going to go to 0 and the M goes to 0 limit, but my signal that I wrote down does not actually go to 0 and the M goes to 0 limit. But that's just a little false. This was the suppression factor taking it to 0. It was multiplying a 1 over M. Why was it multiplying a 1 over M? It was multiplying a 1 over M because, remember, this A naught, did I write it somewhere? No. This A naught goes like root rho over M. So for this formula to be correct, when I took the M goes to 0 limit, I also sent the amplitude A naught to infinity, yeah? If instead I'd written down a formula with A naught in it, you would have seen that it does indeed go to 0 as M goes to 0. So if you actually fix the amplitude of the field and just took M to 0, then indeed this goes over just a constant. It cannot have physical effects. Is that clear? All right, I think that's a good place to stop. That's sort of my introduction to electromagnetic detection. And we will pick up in the next lecture and talk about the last of the couplings. And feel free to come ask questions if you want. Yes?
I'm so sorry about earlier. I actually forgot my glasses.
Oh, no worries. No problem. I know that happens.
But also, can you just explain that last point one more time? I didn't like.
Let me.
Where you're holding